Hi friends, are you ready to learn about relations? We use relations all the time in our everyday lives. For example, relations like Jack is a friend of Jill, 10 is greater than 5, or X is equal to Y, or we have line L is parallel to line M. These are all relations. Relation can describe the connection between two people or two numbers or any two objects. Now, what is the connection between you and me? That's right. Here we have a student-teacher relation. Now, in mathematics, relation is a way to describe a connection between elements of two sets. You studied about sets before, right? So let A be a set of students of class 11 in a school, and B is a set of students of class 12 in the school. Then you can have a relation from set A to set B as A is a friend of B. Now note here, this small a denotes a student from class 11, that is from set A. And when I say small b, it denotes a student from class 12, that is from set B. So we can have where A, that is a student of class 11, is a friend of a student of class 12, that is in B. Or maybe you could have a relation like A is a sibling of B, where A, the student in class 11, has a brother or sister in class 12. Now let's take a look at how we will write relations. Usually when we talk about relations, we talk about the relation between the elements of two sets. So let's say we have two sets here. Set A contains the numbers 1, 2, 3, 4, and set B contains these two numbers 6 and 8. And we have a relation here, A is a factor of B. Now we denote the relation as A capital RB. That's how we write in mathematics the relation ARB. Now we can write the relation in set builder form as A comma B belongs to A cross B, where A is a factor of B. So that's how we write it in this set builder form. And remember, what is A cross B? That's right, it is the Cartesian product of set A and B. And a Cartesian product contains all the ordered pairs A comma B. The ordered pairs that satisfy the relation that A is a factor of B are going to be what? That's right. So look at the numbers here. They're going to form this relation R, which is 1 contains 1 comma 6, 1 comma 8, 2 comma 6, 2 comma 8, 3 comma 6 and 4 comma 8. Because why? You can see where everywhere the first number is a factor of the second number. Now usually in this chapter we will see that the relation is on the elements of the same set. So we don't take two different sets A and B. We have just one set, let's say set A we call it. So R will contain elements from A cross A. So if we consider this set A 1, 2, 3, 4 and the relation A is a factor of B only on set A, then what will the relation contain? That's right, you'll have 1 comma 1, 1 comma 2, 1 comma 3, 1 comma 4 and 2 comma 4. Because notice here these elements where the first number is a factor of the second number. And this is only taken on the set A. The relation is on set A rather than the previous example which was on A involving sets A and B. So usually in this chapter we'll consider the relation on just one set which we are calling as set A. Now let me ask you a question. Can we say that a relation R in set A is a subset of A cross A? Remember what is A cross A? The Cartesian product. So all possible ordered pairs. So what will be the answer here? That is the relation a subset of A cross A? The answer is yes, right? Because the relation usually contains some of the ordered pairs. Now let's go ahead and discuss the different types of relations. As an example, let's consider a set A to be the students in your class. Let's define a relation where the difference in heights of two students A and B is greater than 10 feet. So now can you tell me what will this relation contain? That is, can you find two students in your class where the difference in their heights is greater than 10 feet? Is that possible? No, right? How can you have two children whose difference in height is greater than 10 feet? Absolutely not possible. So then what elements does our relation contain? The answer is nothing. So such a relation is called an empty relation because the relation is empty. It contains nothing. Or it's also known as a void relation. So note it down. Empty relation or void relation contains nothing. So a relation R in a set A is called an empty relation if no element of A is related to any other element of A. And we denote such a relation by the symbol null or phi, you can call it, right? So this null symbol denotes the empty relation. And clearly you can see the relation R, that is this empty relation, is going to be a subset of A cross A. So obviously it satisfies that. If you want to take another example, let's say you take a set A containing the numbers 1, 2, 3, 4. And let's define a relation in A given by the relation R, A comma B, such that A minus B is equal to 5. So can you find two numbers in this set A where A minus B, that is the difference of two numbers, is equal to 5? Clearly you can't find any such numbers because even if you take 1 and 4, the difference is how much? 4 minus 1, 3. So once again this relation contains nothing and we say R is equal to null. So clearly no element A comma B is satisfying the property A minus B equal to 5. So once again this is an example of an empty or void relation in A. Again let's consider a set A to be the students in your class. Now let's change our relation where the difference in heights of two students A and B is now less than 10 feet. So what elements will this relation contain? So if you take any two students in your class, then the difference in their heights will definitely be less than 10 feet, right? So we can consider all possible pairs of students in your class, right? Or even if you take one student, let's call him Arun. Is Arun related to himself? So does Arun comma Arun also belong to our relation here? The answer is yes. Why? Because the difference in height between Arun and himself, so if you measure the difference in height of Arun and himself, how much will it be? It's going to be 0, right? Because Arun equals his own height, which is less than 10 feet. So Arun comma Arun or any student, that is A comma A, will also belong to our relation for all the students. So such a relation will contain all the possible ordered pairs in A cross A. And this type of relation is called a universal relation. So like it contains the entire universe. Of course, the universe restricted to our set A here. So remember, universal relation is a relation R in set A if each element of A is related to every other element of A. That is, R will be equal to A cross A because A cross A is the Cartesian product which is containing all the possible ordered pairs. So this is an example of a universal relation where you have R equal to A cross A. Let's consider another example. Let's take a set A containing these numbers 1, 2 and 3. Now if we define a relation R equal to A cross A which contains 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3, basically all the possible ordered pairs. So this is definitely a universal relation in A. So the empty relation and universal relation that we talked about, they are very simple, right? Empty basically contains nothing and the universal relation contains all the possible ordered pairs. So this is why the empty and universal relations are called trivial relations, because the word trivial means very simple or obvious. So remember, the empty relation and universal relation are together known as trivial relations. Now let's look at identity relations. Once again, we'll take the example as the set of students in your class. And now let's define a relation as has the same student ID number. So that's our relation where it has the same student ID number. Now, which students will satisfy this relation? Remember that student ID number is a unique number given to every student. So a student can only be related to himself or herself because the student ID is unique. So this relation will contain only ordered pairs like A, A, where A is any student. So such a relation which contains only A, A is called an identity relation because you're related only to yourself, to your own identity. So a relation like this, which we denote as IA, is containing A, A for all A belonging to the set A is called an identity relation on A. Let's consider another simple example. Let's say we have a set A containing the numbers 1, 2, 3. Then what will be the identity relation on set A? That's right, it's going to contain 1, 1, 2, 2 and 3, 3 because this will be the identity relation where we have each element only related to itself. And don't confuse this with the universal relation because you can see all possible ordered pairs are not there, right? Only the A, A are there and all of them are there. Such a relation is an identity relation. Now let's talk about equivalence relations. Equivalence relation is a very important relation in this chapter. An equivalence relation is a relation which satisfies three properties. The relation must be a reflexive relation, it should be a symmetric relation and a transitive relation. So only when it satisfies all these properties, we call it an equivalence relation. But hold on. You'll say that what is a reflexive, symmetric and transitive relation? Don't worry, we are going to understand them one by one and then you'll know what is an equivalence relation. Let's start off with reflexive relation. The word reflexive comes from the word reflection. So when you stand in front of a mirror, what do you see? You see your reflection. And who do you see? No guesses here. You see yourself. So in a reflexive relation, every element is related to itself. So let's consider a relation is equal to on a set of numbers A which contains 1, 2 and 3. Now every number is equal to itself. So it will become a reflexive relation that will contain, the relation R will contain 1, 1 because 1 is equal to 1, 2, 2, 2 is equal to 2 and 3, 3. So you can see that this is a reflexive relation. A relation R in a set A is called a reflexive relation. So what is the formal condition? So that if all the A belong to R for all A being an element of capital A. Remember, small a is the element and capital A is the set here. Now for the set A containing 1, 2, 3, let's consider another relation R2 which contains 1, 1 and 2, 2. So is this R2 reflexive? The answer is no, because 3, 3 does not belong to R2. Remember, all the elements have to be covered. So it should contain everything 1, 1, 2, 2 and 3, 3. So R2 is not reflexive just because it contains two of those things. Okay. It should contain 3, 3 also. And now let's consider another relation here, R3, that has 1, 1, 2, 2, 3, 3, 1, 2, 1, 3. Now is this a reflexive relation? The answer is yes, because see, it is covering all the guys that we want, the 1, 1, 2, 2, 3, 3. So all the A is considered in R3. So R3 is a reflexive relation. Now one important note here, don't confuse reflexive with the previous identity relation. Because with this example you can see, is R3 an identity relation? The answer is no, because identity will only contain 1, 1, 2, 2, 3, 3. Right? So identity relations are reflexive. right? All identity relations are reflexive, but as you can see, this reflexive relation is not an identity because it has some extra elements there, right? It has that extra 1, 2 and 1, 3. So note that carefully, the difference between identity and reflexive relation. Here we were talking about reflexive relations. Next, let's look at symmetric relations. Now, what comes to your mind when you hear the word symmetry? The human body is symmetrical about the vertical axis. So the left side is same as the right side. And so many things in nature that are beautiful have symmetry, like butterflies, flowers, starfish, you name it. An equilateral triangle also has symmetry. So guys, what is a symmetric relation? For example, if we consider the students in a class and if we have a relation is a friend of. So if A is a friend of B, then B should also be a friend of A, right? So can you see that the relation is symmetric? A is a friend of B, so B is also a friend of A. So relation R on set A is called a symmetric relation if A is related to B implies that B is also related to A. So when we write it in maths notation, we write it like this: A comma B belongs to R implies that B comma A belongs to R. Note that A and B here, the small a and B, are belonging to our set capital A. Let's consider another simple example with this set A containing the numbers 1, 2 and 3. So if I give you a relation like this, R1, which contains 1, 1, 2, 2, 1, 2 and 2, 1, can you tell me, is this relation R1 symmetric or not? Look carefully. So if you look at this relation, we have to look, remember for symmetric, we have to look at A comma B's and then it should contain a B comma A. So you can see that this relation has 1 comma 2 and it also has 2 comma 1. Hence the relation is symmetric. I don't have to look at that 1, 1 and 2, 2, right? A comma B, the 1 comma 2 is there and 2 comma 1 also belongs to the relation, so it is symmetric. Okay? And note that it does not have 1, 3, it doesn't have to have all of them. What it has, the A comma B, you have to check that the B comma A is also there. So R1 is symmetric. Let's look at another example. Now if I give you this relation R2, this relation contains 1, 2, 2, 1, 2, 3 and 1, 3. Can you tell me, is it symmetric or not? That's right, this relation is not symmetric. Let's look at it why. See, it has 1, 2 and 2, 1. So there the symmetric condition is satisfied. But it has 2, 3 and it doesn't have 3, 2. Similarly, it has the element 1, 3 but does not have the pair 3, 1. So that is why this relation is not symmetric, because remember, if it has A comma B, it must have B comma A also. So R2 is not symmetric. One last example, let's look at this R3. Can you tell me, is R3 symmetric or not? So let's check. See, R3 contains 1, 2 and it contains 2, 1. It contains 1, 3 and it contains 3, 1. Okay. It contains 2, 3 and it contains 3, 2. So see, wherever you're finding an A comma B, the B comma A is there. It also has 1 comma 1, but I don't need to check that, because remember, I have to check the A comma B's and the B comma A's, because if 1, 1 is there, right, if you invert it also, you'll get 1, 1, right? So for the other elements, if you look at it, the A comma B and B comma A is there. So therefore, R3 is also a symmetric relation. Clear? The symmetric relation is crystal clear to you? Now that you know about reflexive and symmetric relations, let's look at transitive relations. Transitive comes from the word transit, which means to go from one place to another. In a transitive relation, if A is related to B and B is related to C, this implies that A is related to C. So it's like you're transiting from A to B, B to C, which means you made your journey from A to C. That's why it's called transitive relation. For example, in a class of students, let's consider the relation is taller than. So let's say if Arjun is taller than Karan and Karan is taller than Mohit, then Arjun has to be taller than Mohit, right? Because Arjun is taller than Karan, Karan is taller than Mohit. So Arjun is taller than Mohit. So taller than is a transitive relation. So remember, in a transitive relation, we write the mathematical notation like this, that if A comma B belongs to R, that is A is related to B, and B comma C belongs to R, right? This implies that A is related to C, which means A comma C belongs to R, where your A, B, C belong to are elements of the set A. Clear? So if A is related to B and B is related to C, this implies that A is related to C. Now let's consider some examples here. So let's say we have this set A containing the numbers 1, 2, 3. And now I give you this relation R1. Can you tell me, is R1 transitive or not? See, R1 has 1, 2. That means 1 is related to 2. 2 is related to 3. So by transitive property, 1 should also be related to 3. Remember, A comma B, B comma C implies that A comma C should be there. And you can see 1 comma 3 is there, right? 1, 2, 2, 3 and 1 comma 3 is there. So this relation R1 is definitely transitive. Now let's look at another example. Let's say I give you this relation R2, which contains 1, 2 and 2, 3. Is this transitive or not? See, in transitive, you have to look at those kind of elements which are of the form A, B, B, C. And here you can see 1, 2 and 2, 3 are of that form because 2 is common, that B should be common, right? A comma B, B comma C. So you have to look for those guys. And both are there, but this should imply that 1 comma 3 should be there. But it is not there. 1 comma 3 is not part of R2. So R2 is not transitive. Clear? Now let's look at another interesting example. Let's say I give you this R3, which contains 1, 2 and 1, 3. Now, is this transitive? You'll say it's not transitive because it is not having that A comma B, B comma C, which implies that there should be A comma C. Because what is the problem here? You don't have those kind of A comma B and B comma C, right? Because you have a 1, 2, but there is no other, ordered pair having or no other relation having 2 in the beginning. So 1 is related to 2, but 2 is not related to anything. Similarly, 1 is related to 3, 1 comma 3 is there, but 3 is not related to anything. But the interesting thing is, guys, the strange thing is, this relation is also considered transitive. But you'll say, why? Because see, transitive relation says that if A comma B belongs to the relation and B comma C belongs to the relation, then A comma C should be part of that. But suppose that B comma C is not there, which is the case here, right? There's no B comma C, that means the relation is transitive. It just contains that A comma B, like there's a 1 comma 2, 1 comma 3, but there's no relations with starting with 2 or starting with 3. So that B comma C is completely missing. So here we don't do that check and we just say the relation is transitive by default or vacuously, it's called vacuously transitive. So I know it is a strange thing because you cannot check the transitivity of this relation, right? Because A comma B, B comma C both have to be there, which is not the case here. So remember this case, in this kind of relations, do not say not transitive, it is transitive by default. So if I summarize the transitive relation for you, what will we say? That if A is related to B and B is related to C, that is A comma B and B comma C are both part of the relation, then you need to check if A comma C is there or not. That is A related to C or not. If it is there, then the relation is transitive. But suppose you have in your relations only A comma B's, right? And there is no B comma C. Then we also say the relation is transitive by default. So remember these things, right? So these are the important checks that you need to do for your transitive relations. Now that we've learned what is a reflexive, symmetric and transitive relation, we are confident of defining what is an equivalence relation. A relation R in a set is said to be an equivalence relation if it satisfies all the three properties. Remember, the relation should be reflexive and symmetric and transitive. So it has to satisfy all these three properties, reflexive, symmetric and transitive. Then we call it an equivalence relation. Because if any one of these fail, it will not be an equivalence relation. So to prove it, you have to check for all these three properties. Now that you know the concept of relations, let's practice some sums on this topic. Here's the first question. Show that the relation R on this set given to us 1, 2, 3 given by this relation. So we've been given a relation here and you can see it's in roster form 1, 1, 2, 2 and so on. We have to show that this relation, it is reflexive, but note it is neither symmetric nor transitive. So what do we have to prove? That this relation is reflexive, but the relation is not symmetric, not transitive. So let's start with the reflexive property. Remember what is that reflexive property? Like you're seeing your reflection in the mirror. So that's right. Those elements A, A have to be present in our relation, right? For all A. So our set is 1, 2, 3. So for these elements, that means 1, 1 should be present in the relation, 2, 2 and 3, 3. So let's check it. So do we have that? Absolutely. You can see 1, 1 is present in the relation, 2, 2 is also present, 3, 3. So what do you think? Is the relation reflexive? Yes, right? So we can say that given all these are present, A, A belongs to the relation for all your A. So therefore we can see the relation is reflexive. Now the next thing we have to prove is that this relation is not symmetric, not transitive. So what is the symmetric property? Remember, in symmetry, if A, B belongs to the relation, B, A should also be part of the relation, right? So we need to check that here. So let's say we have 1, 2 is there in the relation, right? But is 2, 1 there? No. Similarly, you'll say 2, 3 is there, but 3, 2 is not there. But you don't have to check more than one, right? So if we have got one pointer that 1, 2 is there, but 2, 1 is not there, we are done, right? We have disproved we have proved that it is not symmetric. Clear? So basically we can say that 1, 2 is part of the relation, but 2, 1 is not part. So not an element. This is how we represent, right? Is not an element of the relation. Therefore, R is not symmetric. Simple. So if you find one case which proves it against it, right, it is not symmetric. Similarly, check for transitive. So in transitive, what do we have to check? Remember, A, B belongs to the relation, B, C belongs to it, then A, C should be part of the relation, right? So let's take a look here. So if you guys see, we have, so let me first write that down, the transitive property. So in the transitive case, remember, we have to look for these kind of pairs, A, B and B, C part of the relation. Then we have to check that A, C is there. So this is one very important thing in transitive. Remember, this B element is common, right? It should be the second guy in this A, B and the first guy in this B, C. So you have to look for pairs like that. So if you see here, we have 1, 2, right? See, this 2 is common and 2 is common. So 1, 2 is like my A, B. So let's write that here. So we have 1, 2 as part of the relation and we have 2, 3 also as part of the relation, right? So see, 2 is common. That means if it is transitive, what should be part of the relation? That's right. 1, 3 should also be part, right? Then only it will satisfy. So this implies that 1, 3 should be there. But is 1, 3 in the relation? Check. The answer is no, it's not there. So 1, 3 does not belong to the relation. Therefore, R is not transitive. And again, we have proved it for one case. For this one case we have proved, we don't have to check for other cases. It's done, right? So that means this relation is not transitive. So simple, this is how you solve this question where we have proved it's reflexive, but neither symmetric nor transitive. And I'll also show you the formal working out here. So there you can see the same thing we have done here. So you can see that this relation for reflexive, we have to prove that all the A, A's are there, right? For all the elements. So 1, 1, 2, 2, 3, 3, we have proved that. Not symmetric, we proved with this case, remember, 1, 2 belongs to the relation, but 2, 1 does not. And transitive property, we use this 1, 2, 2, 3 belongs to R, but this guy is not there. So it is not transitive. Clear? So simple question, just apply the properties and you're done. Here's our next question. Let Z be the set of all integers and let R be the relation in Z defined by, this is our relation, A comma B, where A minus B is even. And they're asking us to show that R is an equivalence relation in Z. So guys, do you remember what were equivalence relations? It had to satisfy three properties. What are the three properties? That's right. The relation has to be reflexive, symmetric, and remember, transitive. So we have to prove all these three properties, then only we are confident that this relation is an equivalence relation. So let's start off with the reflexive property. So how will you prove this? Again, to get a feel of the relation, you can think of some numbers, right? Like for example, if I say to prove that this is a reflexive relation, so let's do the first part. We have to prove that it is reflexive. That means all the A comma A's should belong to the relation, right? A comma A's should belong to the relation. And we said that Z is a set of all integers. So this relation is on a set of all integers. So let's say if I tell you some integer like 2, right? So if you take an integer like 2, then 2 comma 2, does it belong to the relation? Let's check. 2 minus 2 is how much? So if you take the number 2, we know that 2 minus 2 is 0. Or if you take the number, let's say minus 5, so minus 5 and minus of minus 5 is 0. So always when you take a pair like A comma A, what will it turn out to be? When you find the difference A comma B, A minus A is going to be 0. And clearly 0 is it's an even number, right? So 0 is considered even because 0 is divisible by 2. So therefore we can clearly see that this is always even. So for any A comma A that you take, it is definitely reflexive. Okay. So you can get an idea with the basic numbers, and then this is what you need to show, that if I take any A comma A, the difference is going to be 0. So therefore the relation is definitely reflexive. That part is done. Next, let's look at the symmetric part. How do you prove that it is symmetric? Remember, what is the condition for symmetric? You have to show for symmetry. So let's do the symmetric case. For symmetry, we have to show that if A comma B belongs to the relation, then B comma A should also be part of the relation, right? So again, take some sample numbers just to think it out, right? So if I say that 4 comma 2 is belonging to the relation, right, where 4 minus 2 is even, right? So you have to choose such numbers where 4 minus 2 is even, right? So you can see 4 minus 2 is 2, that is even. Then will 2 comma 4 belong to the relation? So here you can see 4 minus 2 is equal to 2. Yes, this belongs to the relation. Now you have to prove that 2 comma 4 should belong to the relation. Then it will be symmetric, yes or no? Okay. So if I check for 2 comma 4, what will it be? Is it belonging to the relation? It should satisfy this condition. So here we have 2 minus 4, and that you can see is minus 2. Now is minus 2 an even number? Don't get scared when you see that negative sign. Minus 2 is divisible by 2, right? So it is even. So this number is even. Therefore 2 comma 4 is also part of the relation. Any pair like this you take. So this is where you're thinking in terms of examples. But when you're writing it out, you can say that if A minus B is even, basically what we have to do in B comma A, we have to check, is B minus A also even? How will you prove that? Are you getting the point? If A comma B belongs to the relation, A minus B is even. So this we are known, right? I've taken a comma B so that it A minus B is even, it belongs to the relation. Now if I do B minus A, what will that be? B minus A is going to be, I can write it as negative of A minus B. Check. See? Minus B plus A, right? Minus A plus B, right? The minus becomes. So B minus A is minus of A minus B, which is negative of an even number by the relation. So that is also even. So see, whenever A minus B belongs to the, A comma B belongs to the relation, B comma A will also belong. So therefore, definitely the relation is symmetric. So two things are done here. We have to do the last one, which is transitive. For transitive, what do you have to take? A comma B, B comma C part of the relation, then A comma C should also belong to the relation, right? So let's do our third case, which is transitive. Again, to understand, you can think of some example. So let's take some numbers like where you have, let's take 4 comma 2. So 4 comma 2 belongs to the relation because 4 minus 2 is even, right? It's 2. So 4 comma 2 belongs to the relation. Then if I take some numbers like A comma B, B comma C, right? So I have to take over here 2 comma, let me take 10. Does 2 comma 10 belong to the relation? Yes, because 2 minus 10 is minus 8, which is even. So this is also belonging to the relation. Now you need to check, see, this A comma B, B comma C, is A comma C belonging to the relation? Does 4 comma 10 belong to the relation? Check. Is 4 comma 10 part of the relation? Yes, because 4 minus 10 is minus 6, that is also even. So see, this belongs to the relation. So whenever you take these kind of pairs, you will always see that the final difference of A comma C will also turn out to be even, hence belonging to the relation. But again, this we cannot write just example, right? We have to express it mathematically. So we say if you take A minus B is even and B minus C, in B comma C, B minus C is even. So we have to prove that A comma C, that means A minus C is even. This is what we have to prove for transitive, right? So how will we do? Simple, you just add these two up. When you add these two up, if I add these two, what do I get? Minus B and B will get cancelled. So on the left hand side, I'll get A minus C. And what is an even number plus an even number? Tell me. When you add up two even numbers, you always get an even number. So there you can see A minus C is even. We have proved it. Clear? So this is how we have also showed that the relation is transitive. So we have proved relation is reflexive, symmetric, transitive. We are done. That means therefore relation is equivalence relation. This relation where, what is the relation? That if you take A comma B is, then A minus B is even. That was this relation is definitely equivalence relation. And see, I'll show you the formal working. This is how you should write it out formally. That's where I explained you. So here you can see that for proving your reflexive, you can see that any two elements you take, the A comma A you take, A minus A is always 0, which is even. So relation is reflexive. Similarly, if you take A comma B and B comma A, you can see that they are just basically the negative inverse of each other. So that is also even and hence symmetric. And last but not least, your transitive case, which we showed. If you take A minus B and B minus C, you add it up, what you are left with? A minus C, which is also even. So relation is also transitive, hence it is an equivalence relation. Clear? Simple, you guys can do it, confident? So that's all. But it's a lot of stepwise, otherwise you can see it's very easy to solve. Here's the next question, and it's a real interesting one. So here it says relation R in the set A of all human beings are the following relations equivalence relations. So let's consider the first one. It says consider x comma y relation, right, where the relation is x comma y, where x is exactly 7 centimeters taller than y. So you have to consider two people, x and y, where the first person is exactly 7 centimeters taller than the second person. Have you understood the question, right? So you're considering two people, right? So we can draw two people here. I'm not a great artist, but I'll try to draw something here. So basically you can see that these are the two people, okay? This is x, this is y, and it says x is exactly 7 centimeters taller, right? So now is this an equivalence relation? Again, for equivalence relation, we have to show all the three properties: reflexive, symmetric, transitive, okay? Now the question is this relation reflexive? For reflexive, what do we have to show? A comma A belongs to the relation. So if you consider like this person x here, so x comma x, will it be part of the relation? So will x comma x, will it belong to the relation? That means, can a person be 7 centimeters taller than himself? Because x comma x means you're considering with himself, right? The reflection. So will x comma x belong to the relation? No. How can you be 7 centimeters taller than yourself? So this is not part of the relation. So hence we can say not reflexive. And so if this was an objective type question, you would have said, you would have stopped there only. Because if the relation is not reflexive, it cannot be an equivalence relation. But usually in the school you'll show, or you can check with your teachers, you have to show the working of the other two also, right? You have to check for symmetric and transitive. But we definitely know it's not reflexive. Now let's check for symmetric. Very interesting. Again here what will you say if x comma y belongs to the relation? So we have some person which is 7 centimeters taller than the other person. Will the second person, will y comma x belong to the relation? Then how can y be 7 centimeters taller? Right? X is 70 centimeters taller, that it's belonging to the relation, but y comma x cannot be part of it. So therefore we know that this is not going to be symmetric. That's gone. And the last part is transitive, right? In transitive we have to consider three people, a comma b, b comma c, and check for a comma c, right? So in transitive case, what is the situation we'll have? So if I say that I have these two people, x is 7 centimeters taller than y, so they are belonging to the relation, and then let's consider another person z, who's shorter here. So see 7 centimeters, this is the difference here, and y is 7 centimeters taller than z, so he's belonging to the relation. Now the question is x comma z part of the relation? So x is definitely taller than z, right? But by how much? 7 plus 7, 14 centimeters, right? Because x is taller than y by 7, y is taller than z by 7, so x is taller than z by 14 centimeters. Clear? So will it belong to the relation? Absolutely not, because the relation says exactly 7 centimeters taller, not just taller, right? So we can see over here that x comma z is not part of the relation, unfortunately, so it is going to be not transitive. Clear? So yes, we could have stopped here itself, but we showed that relation is not reflexive, not symmetric, not transitive, therefore definitely not an equivalence relation. Clear? And again I'll show you the formal working. So this is how you write it out, where you have shown clearly that x comma x cannot belong to R, so not reflexive. Same way you have shown x comma y, if it belongs to R, y comma x cannot belong to R. Oh, so there should be a cannot over here, right? So this should be not symmetric. Clear? And same way we can see that x comma z cannot belong to R if x comma y and y comma x are part of the relation, y comma z, sorry. So it is not transitive also. So clearly this is not an equivalence relation. Simple. Now let's look at the second question. This is also an interesting one, x comma y, where x is a wife of y. So this is like the real, the relations what we use in our everyday life, right? Brother-sister relation, husband-wife relation. So they are asking, is this an equivalence relation? So you have to think of examples again, right? So here, there's not much maths to do, it's more with the language. So x comma y, where the relation is x is a wife of y. So will it be reflexive? Reflexive means x comma x or a comma a belong to the relation. Does it belong to the relation? Check. Is it part of the relation? Can you be a wife of yourself? That sounds funny, right? That sounds strange. So this is not possible. It is not part of the relation. So we can say it is not reflexive, right? So relation is not reflexive, not possible. How about symmetric? So if I say x comma y, that means x is a wife of y, okay, that's part of the relation. Then can I say that y comma x belongs to the relation? What do you think? So x is a wife of y, right? But can y be a wife of x? But here x is a wife of y, so x is the female, this guy is the male, right? So this is the wife, y is the husband. So how can husband become the wife of x, right? He's the husband of x, he's not the wife of. So again, it's a play of language and it's not part of the relation. So don't think, yeah, no, they're the couple, right? No. So this is going to be not symmetric. Now let's look at the transitive property for this x is wife of relation. So we'll start off with x is wife of y, okay. That means x comma y belongs to the relation, if you consider some example. Now the question is, will y comma z be part of the relation? Yes or no? Tell me. Will y comma z be part of the relation? So suppose you say y comma z, that means y is wife of z. Can we put this part of the relation? See, the problem here is x is wife of y, that means x is female, y is male. Now if I say y is wife of z, this is a male. Male cannot be wife of z, right? By our language, male cannot be the wife of z. So here this will be wrong. That means y comma z does not belong to the relation. It cannot be part of the relation. So does that mean it is not transitive? Hold on. Remember what I taught you? Transitive has that dangerous thing that only if both exist, x comma y and y comma z exist, only then you have to check x comma z exist, right? And then prove it is transitive. So note here, if x comma y and y comma z are both part of the relation and x comma z is not, then we say it's not transitive. But here the problem is x comma y belongs to the relation, but there's no chance of y comma z being there. So we don't have to check. That check is not required, right? So this is not part of the relation. That means if this y comma z is not there, there's no need to check for transitivity or transitive nature of the relation, and then we say the relation is transitive by default, right? Or vacuously transitive. Remember that dangerous thing? So this relation is transitive by default because only this belongs to the relation and this doesn't. So we say it is transitive by default. Okay, so this was a little dangerous case where it looked like, hey, it's not going to be transitive, but it is. So this relation is not reflexive, not symmetric, but it is transitive. And let's look at the formal way of writing this stuff. So as you can see, we discussed that this relation is not reflexive because x comma x cannot belong to the relation that we have discussed. It is not transitive because you can't have x as wife of y, y cannot be wife of x, so not symmetric. But the transitive is important one because we said x comma y is part of the relation, but this guy does not exist as part of the relation, so it is transitive and truly by the maths language by default. Okay, but just because it is transitive, it does not mean it is equivalence, because equivalence means all three properties have to be satisfied. So we end up saying it is not an equivalence relation. Clear? Now let's look at the third question, which is a very interesting one. The relation is x is a father of y. So where you have these pairs x comma y of human beings, right? Where x is a father of y. So this one I want you to try as your homework question, right? So try out this homework question and let me know in the comments below, not only that is it equivalence or not, you have to tell me whether is it reflexive or not, symmetric or not, or transitive or not, again using the language, right? That think of the example x is a father of y, right? And all those cases. So this is going to be your homework question, try it out. And guys, do let me know your answers by putting it in the comments below. I look forward to reading your answers and I promise to reply to them. I hope you enjoyed this video and the topic of relations is crystal clear to you now. And do check out the courses on our website manochaacademy.com and our Android app Manocha Academy. Links are given below. We have courses on physics, chemistry, biology, maths, coding and artificial intelligence. In these courses, you'll get concept videos, live classes, quizzes, questions, mock tests and revision notes. So they will be perfect for your exam preparation. All the links are given below, so do share it out with your friends. And do remember to hit the like button and share out this video with all your friends. And if you still haven't subscribed to our YouTube channel, come on, what are you waiting for? Go smash that subscribe button right now and click on the notification bell so that you don't miss out on any of our videos. So stay connected and related with Manocha Academy and just keep learning.